This video will be additional homework problem solutions for section 5.6, integration by parts. I'll start with problem number 7. Problem 7 says the integral of x squared sine pi x. Dx. When we integrate by parts and we have a power of x, our approach is to allow the power of x to be u. Remember, our first step is to find u and define dv. U is something we know we can differentiate. dv is something we know we can integrate. So we're going to let u equal x squared, and we're going to choose for our dv sine pi x dx. We then calculate du. We take the derivative of x squared. We get 2x dx there. We integrate sine pi x. Sine pi x is going to be a u sub. We're going to let u equal pi times x. So du would be pi dx. So we would need an additional factor here of pi before we could integrate, which means we would balance that out in front of the integral with a 1 over pi. So that integral would look like 1 over pi, the integral, sine pi x, pi dx. That would then turn into 1 over pi, the integral. This is our u, this is our du, and we would have the integral of sine u du. And when we integrate that, of course, we get negative cosine of u. So this would be negative. We don't want to lose our 1 over pi. We would get 1 over pi. There would be a minus sign because the integral of sine is going to be negative cosine of u. In this case, our u is pi times x. So we're ready now to proceed with solving our integral. Remember, to solve an integration by parts, we rewrite the integral. Then we say that's equal to uv minus the integral of v du. That's our formula for integration by parts. And we have all of our components right here in our table, neatly organized. So this is going to be u times v. So that's going to be negative 1 over pi times u, that's x squared. And then we have cosine of pi times x. Minus the integral of v. V already has a negative sign, so that's going to turn that into a plus. Two negatives make a positive. We're going to get the integral. Well, let's go ahead and put the constant out front, huh? Let's do that. So we're going to have plus. Our constant is 1 over pi. We have the integral. And then we have v, which is cosine pi x. So that's going to be cosine of pi x times du. Now du is going to be 2x dx. Now we're going to rewrite this integral in a more traditional looking format. This is done. This is going to be minus x squared over pi cosine of pi x. Here we're going to have plus. 2 is a constant, so we're going to bring that out front. We get 2 over pi. We have an integral now, and we have our x. We normally want to put our x terms in front of our trig functions, and then we have cosine pi x dx. So we have another integral to solve, but this integral is in the format or in the form of being solved using integration by parts. So we're going to do a second integration by parts problem inside our current integration by parts problem. I'll switch over to different color. I'll use green And we'll do this problem here in green. So this answer is done. So we're just going to kind of flow this rest of the problem over here, and then we'll write the final result down here on the board. To do this problem, we're doing integration by parts. So we're going to let u equal x because we have a power of x. We're going to let du equal cosine pi x. We're going to let dv equal cosine pi x dx. Again, we differentiate our u to get du. That's going to give us dx. We integrate here. We have cosine of pi x. We just integrated sine of pi x. This is of the same structure, the same form as this. So we're going to go through a very similar process. We're going to end up, in other words, with a constant of 1 over pi out front. And then when we integrate, right, instead of a sine u, it would be cosine u. The integral of cosine is positive sine. So we get sine pi x right here. We don't have to play with that negative. So when we come over here, we're going to have plus. And now we're going to have 2 over pi times uv minus the integral of v du. That's going to give us plus. This is the 2 over pi right here. Bringing our constant down. U times v is going to be 1 over pi times our x times our sine pi x minus the integral. Now our integral is going to be v du. So we're going to have a 1 over pi as our constant. We're going to have the integral. We're going to have sine pi x. And we're going to have dx. Now, don't forget, all of that is multiplied by 2 over pi. So here we're going to have plus, and we're going to have 2 over pi squared when we distribute, x sine pi x, right? That part's done. Here we're going to have minus 2 over pi squared. Again, distributing from here to here. The integral of sine pi x, we've already completed that integral. We did the integral of sine pi x way back here in the beginning, and we know that's a u sub, and it turns out to be negative 1 over pi cosine pi x. So we know how to integrate this from up here, and so here we get negative 1 over pi cosine pi x, and now we'll add our constant of integration plus c. So our final answer, right? Don't forget this component, this term here. We're going to have negative x squared over pi cosine of pi x. From here, we're going to have plus 2x over pi squared sine of pi x. And over here, we're going to have a negative times negative. So we're going to get a plus 2 over pi cubed. And we're going to get cosine of pi x plus c. So that's number 7. So here we had to do an integration by parts. And then within our integration by parts, we had to do a second integration by parts. All right, so that's number 7. Because this recording is going to get long, I'm going to pause it in between every time I have to erase. So I'll be right back, and you'll see a lot of gaps in the video from here on in, but I don't need to spend the time recording my erasing. Okay, we'll pick up here with number 12. Number 12 is the integral of inverse sine x dx. All right, the integral of inverse sine x dx. Now, when we get a problem of this type, and we look at this kind of a problem, and we think to ourselves, well, there's only one function. Is this really going to be an integration by parts question? And the answer is going to be yes. We're going to do this with integration by parts. And so when we get a situation like this where there's only one function, we still are going to find our u, and we're still going to find our dv, and we're going to ask ourselves, what do we have? It's sometimes, right, when this is a case, we're going to well, it would make no sense. Let's start with that observation. It would make no sense to call dv inverse sine x dx. Why would that make no sense? Well, because our next step then would be to find v, and to find v, we would have to take the integral of this. Well, that's our original question. That's what we're trying to answer. We don't know the integral of that. So it makes no sense logically to put the inverse sine there. So the only alternative is to put the inverse sine here. Now, what does that leave us for dv? That just leaves us dx. Now, our next step is to find the derivative of inverse sine, right? We're supposed to remember the derivative of our inverse trig functions. If you don't remember the derivatives of any function from Calc 1, if you don't, you get to a problem like this, you're like, oh, I don't remember that derivative. Of course, you can look them up in the book. In the book, they're there. But there's a table of derivatives in the back of your book. There's a table of integrals. Pardon my book, it's falling apart. But there's also a table of integrals, and you can look up inverse trig functions right here. Formula number 19 says the derivative of inverse sine is 1 divided by the square root of 1 minus x squared. Okay. So we know this is 1 divided by the square root of 1 minus x squared. When we integrate dx, right, integrate dx, we're going to get x. The integral of dx is just going to give us x. So now we're ready to proceed. We have the integral, we have sine inverse dx. That's going to be u times v minus the integral of v du. So when we plug everybody in, that's going to be u times v. U times v is going to be x inverse sine of x minus the integral of v du. That's going to give us x, right, for v. Du is going to give us the square root of 1 minus x squared. And then when we took the derivative here, I left out the dx. So there's our dx. Now that's an integral we can solve. I know it looks hairy. It looks kind of, maybe if you've moved forward in the book and looked at trig substitutions, it may look like a trig substitution problem because it has of the form 1 squared minus x squared, but it's not. It's just a simple u sub here. We're going to let u equal 1 minus x squared, and then du is going to be negative 2x dx. And so we'll look at our integral and we'll think to ourselves, well, we need a negative 2 right here with our dx, and we balance that by putting another negative and its reciprocal, negative 1/2 out front. That gets us, if we look at this integral now, we have plus, we have 1/2, we have the integral, we have negative 2x on top, and we have our square root of 1 minus x squared on the bottom, and we have dx. The negative 2 dx is our du. The 1 minus x squared is our u. And so this integral transforms itself when we do our u sub into 1/2 the integral. This is going to be du. We can put that negative out front now. And we're going to have the integral of 1 over the root of u du. But we know that to be minus 1/2 the integral of u to the minus 1/2 du. So we're just taking the integral of u to a power. Remember, when we integrate, we add 1 and divide by the new integral. So this is, the new exponent. This is going to be minus 1/2. We add 1 here. That gets us u to the positive 1/2. We divide by 1/2, which is the same as multiplying by 2. Tack on our constant. And now we're ready to resubstitute back into our expression our value for u. Don't forget to drop this down to your answer. So we have x inverse sine of x. We now have minus 1/2 times 2. So that's really going to go away, isn't it? Negative 1/2 times 2 is just going to be 1. And we have u to the 1/2. That's going to be the square root of 1 minus x squared plus c. All right, so that's problem 12. Picking up with problem 15. Problem 15 is a definite integral. It's the integral from 0 to pi. So we'll have to evaluate this one at the end of this using our evaluation theorem. And then we have t sine of 3t dt. Again, we're going to let u in this case equal just t. It's a power of t. dv is something we can integrate, and here we're going to have sine of 3t, which we've done an integral of that form many times. We know that's going to be a u sub. When we take the derivative here for du, we get dt. When we integrate this, the integral of sine is negative cosine, so we're going to get our negative 1/3 from our u sub, and we're going to get cosine of 3t. So we have all of our components ready. So we're going to rewrite this. We have the integral from 0 to pi t sine 3t dt equals uv minus the integral of v du. When we plug everybody in, we have u times v, so that's going to be minus t over 3, t times 1/3, cosine 3t, negative from here, right? So it's minus. Then we have a minus on our integral, but we have a minus on our v, so that's going to make that a plus. And we have the integral of v du. I left out the 1/3, so let's erase this. Seems to be a very consistent mistake I make. I seem to leave that constant out every time. So we have, I got the negative sign though. So we have the negative, and the negative makes a positive 1/3. We have v du. So we get the integral, we get cosine 3t dt. This is just a straight u sub. We can do this almost, well, I'm going to do it without doing any work at this point because I've showed it to you multiple times. So we get this term plus, right, plus. We have our 1/3 here, but we know when we integrate cosine 3t, we're going to get another 1/3. So that's going to turn into 1/9. The integral of cosine is positive sine. So we get sine 3t plus c. So that's number 15, all right? Without doing the u sub in detail, because we've done the u sub on previous problems over and over and over again. Okay. If we do problem 16, we have another definite integral. We have the integral from 0 to 1. Oh, I never evaluated problem 15. Well, I forgot about that step. So that one you're going to have to do on your own. I apologize for that. I was so excited about being done. I completely forgot that it was a definite integral. I forgot to evaluate it. Okay. So what about 16? It's a definite integral, and this time I'll remember to evaluate it. So we have the quantity x squared plus 1. Then we have e to the minus x dx. Okay. So instead of just having a power of x, we actually have a binomial. We have x squared plus 1. Now, there's a couple of ways we can go about solving this problem. One, we can just think to ourselves, well, you know, maybe I'll just do what I've been doing. I'll go ahead and let u equal x squared plus 1. I'll let dv be e to the minus x dx. Now, if we do that, du is going to be 2x dx. The derivative of 1, of course, is 0. When we integrate this, the integral of e to the minus x is minus e to the minus x, right? By we would do a u substitution there to get that. And if we just take this approach, things look like they're going well for us. So if we rewrite this, the integral from 0 to 1, x squared plus 1, e to the minus x dx, that's going to be uv minus the integral of v du. So what do we get? Well, we plug in u is x squared plus 1, v is minus e to the minus x. So that's going to give us a negative x squared plus 1, e to the minus x. Now we're going to have, that's finished. We don't have to do any more work. So I'm going to say I'm going to evaluate that between 0 and 1. So this time I won't forget to do that stuff. Minus the integral of v du. Now v is a negative, so that negative makes this a positive. Du has a 2 in it, right? A 2. So we'll put that 2 out front. We get the integral from 0 to 1. Now we have an x from here. We have an e to the minus x from here, and here's our dx. Well, that's an integration by parts integral, right? That's an integral we've seen prior to this, and we solved that using integration by parts. So I'll change colors. I'll come over here. I'll use brown. U equals x. dv equals e to the minus x. Of course, the derivative here is going to be dx. Here, we just did this up above. And we're going to get ourselves minus e to the minus x. So this term here is going to be plus 2 times. And then we're going to have our uv minus the integral of v du, right? We're going to use our formula again. uv is going to be negative x e to the minus x. Now that's completed. Minus, right? Minus, but we have a negative here, so it's going to turn to a plus v du, and that's just going to be the integral of e to the minus x dx once we adjust for the negative and the negative in our integration by parts. If we go ahead and write this out now, we're going to have plus, well, if we're going to write it all the way out, we should just do the multiplication. So we're going to have minus 2 from here, x e to the minus x. We're going to evaluate that between 0 and 1. Here, we're going to integrate this. We know what the integral of e to the minus x is. We've done it twice already. It's going to give us a negative e to the minus x times our positive 2 is going to be minus 2 e to the minus x, and we're going to evaluate that between 0 and 1. And we can go ahead and drop down our first term here. That's minus the quantity x squared plus 1 e to the minus x evaluated between 0 and 1. So if we go through the evaluation steps, right? If we go through the evaluation steps, we're going to plug in 1. 1 squared is 1 times, 1 squared is 1 plus 1 is 2. We have a negative 2 there. And we have e, we put 1 here, right? And we have e to the minus 1. Here we're going to put in a 1. We're going to have negative 2 times 1 times e to the minus 1. Here we're going to put in a 1, and we're going to get another negative 2 e to the minus 1. So that's our f of b, right? When we do our evaluation theorem, we have f of b minus f of a, our antiderivative evaluated at b, the upper bound, minus the antiderivative evaluated at a, the lower bound, minus the antiderivative evaluated at the lower bound. All right, so don't forget that part. We're going to plug the 0 in here. We get 0 squared, that's 0. Plus 1 is 1. E to the 0 is going to be 1. Don't lose this negative sign. We're going to get negative 1. Here we're going to plug in 0 for x. So negative 2 times 0, that's going to be 0, so that term goes away. Here we have a negative 2, and we have 0 here for x. That's e to the 0. That's 1, so that's going to be negative 2. Now, if I haven't butchered the negative signs, and there's no guarantee that does not happen, so if it has, I apologize. We have negative 2 e to the minus 1, negative 2 e to the minus 1, negative 2 e to the minus 1. That's going to be negative 6 over e. Here we have negative 1, negative 2. That's negative 3 with a negative sign, so we get plus 3. And again, if I haven't butchered a negative sign someplace, that's going to be our answer, number 16. Okay, next problem on the list is number 17, another definite integral. It's the integral from 1 to 2 of the natural log of x divided by x squared dx. Now, when we make our choices for u and v here, we're going to have to go back to our foundational approach. We're going to look at this. We're not just going to go, oh, that's an x, I'll put it here. We're going to have to ask ourselves, what can I take the derivative of? What can I integrate? We don't have an integral formula for the natural log of x. Well, nobody in Calc 1 taught us how to integrate the natural log of x. We don't have an integral formula for that. So we can't put that there, which means by default, it has to go here. Now, this is x to the -2, right? We know how to integrate x to the -2, so we'll just put that over there. When we get to these problems that, have what I would say non-traditional pieces that don't look like all the examples in the book, then we just think our way through it, right? We can do this. If I take the derivative of the natural log of x, I get 1 over x dx. This is u to the -2. If I integrate that, I add 1. So that's going to be, sorry, that's not u to the -2. It's x to the -2. So I'm going to get -1. I divide by -1, so I get minus x to the -1. Now I rewrite this integral from 1 to 2, the natural log of x over x squared dx. That's going to equal uv minus the integral of v du. U times v is going to be, now this is really minus 1 over x, right? If we rewrite that, so u times v is going to be ln of x over x with a minus sign, and we're going to evaluate that between 1 and 2. It's done. We can put the evaluation in there. It's going to be evaluated between 1 and 2. Minus the integral of v, which has a negative sign, so that's going to be a plus. That's x to the -1 times du, which is another x to the -1 dx, and that's going to be evaluated between 1 and 2. So this is going to be minus the natural log of x over x evaluated between 1 and 2. This is going to be plus the integral from 1 to 2 of x to the -2 dx. We've already integrated that once today, right? I mean, once in this problem, we integrated it right here. So we know what we're going to get. We're going to get here minus the natural log of x over 2 evaluated between 1 and 2. The integral of x to the -2 is minus 1 over x. So that's going to turn this to a negative 1 over x evaluated between 1 and 2. When we do our evaluations here, we're going to plug in 2. So we're going to have minus ln of 2 over 2 minus, when we plug in 1, right? We plug in 1. The natural log of 1 is 0. So that's going to be 0 divided by 2. That's going to be 0. Minus, when we plug in 2 here, we're going to get a half. Minus, when we plug in 1, we're going to get 1. So what do we have? We have a half minus 1 with another negative. That's going to be positive 1/2. And here we have minus the natural log of 2 over 2. All right, so that was number 17. Don't let logs scare you, right? Remember, the only thing you can do with a log is take its derivative. You don't know how to integrate it. So the only thing you can do with it is take its derivative. Okay. Now we'll look at number 23. 23 looks very intimidating, right? It's the integral from 1 to 2. It's our friend, the natural log of x. That's squared, and then this is dx. But to do this problem, again, we have to remind ourselves, when I'm choosing my u and I'm choosing my dv, dv is supposed to be somebody we can integrate. We don't know how to integrate the natural log of x. So that's going to have to be u. Now it's going to be a chain rule problem. dv is going to be dx. I don't know why I wrote that. And which means v is just going to be x. Now du is going to take a little bit of work. We're going to bring down the 2 using the chain rule, natural log of x to the first, times the derivative of what's inside. That's going to be 1 over x. Okay. times dx. There's no reason to panic about it. We'll just do it and see what's going to happen. This is the integral from 1 to 2, natural log of x squared dx equals uv minus the integral of v du. It wouldn't have given us a problem. It doesn't work. So we just have to have faith that it's going to work out. U times v is going to be x times the natural log of x squared. We're going to evaluate that between 1 and 2. Okay, we can already put that down. That part's done. There's no integral left there. Minus the integral from 1 to 2. And what do we have here? We have v du. All right, we can write the whole thing out. We have 2, we have ln of x, we have 1 over x, we have dx, and we have x. Well, the x times the 1 over x is 1. The 2 goes in front, so we have minus 2 times the integral from 1 to 2 of the natural log of x dx. I did that integral for you in your notes. Right, I showed you how to do that. It's an integration by parts problem. We'll go ahead and change colors here because we're doing a different component and other parts. So here, remembering the same thing we set up here, the only place we can put the natural log is right there because we can't take the integral of the natural log, which means dx goes here. That gives us v is x. The derivative of this, of course, is 1 over x dx. We just have to trust that it's going to work. So we're going to get minus 2 times uv. So that's going to be x ln of x. That's done. So we can put down our evaluate between 1 and 2 minus, it's not a bracket, minus the integral of v du. So that's going to be x times 1 over x. That's 1. So the only thing we have here is dx, and that's evaluated between 1 and 2. Well, that integral is easy. So what do we have now, right? If we go back to our brown color, because we're going to write the whole problem out. We have x ln of x, that is squared. We're going to evaluate that between 1 and 2. Here we're going to have minus 2, right, times x ln of x to the first, and we're going to evaluate that between 1 and 2. Here we have a minus times a minus, that's going to be plus 2. The integral of dx is just x, and we're going to evaluate that between 1 and 2. Now, if we take a look at what we're given here, we're given a gift, right? Here's a natural log, here's a 1. The natural log of 1 is 0. When I square that, I get 0. Here's a natural log, here's a 1. When I plug that in, that's going to be 0 as well. So when we plug in a 2, we're going to get 2 ln of 2 squared. So 2 ln of 2 squared. When we plug in a 1, we're going to get 1 times the natural log of 1. That's 0. 0 squared is 0. That's going to be 0. That's gone. Here we plug in a 2. We get 2 ln of 2 times negative 2. So we get minus 4, right? Because there's going to be a 2 here. 2 times 2 minus 4 ln of 2. Here we get 2 times 2 is 4, right? We plug in a 1. We got to subtract f of b minus f of a. We plug in a 1. We don't get a 0 here. We get a 2. And so our final answer is going to be 2 ln of 2 squared minus 4 ln of 2 plus 2. Problem works out to be, honest to goodness, shorter than some of the problems we did previously in this homework assignment. But it just looked nasty because it came with a natural log. And whenever we see a natural log, you know, our first instinct is to get kind of nervous instead of just thinking, oh, I can do that. Okay, I'm going to end the recording here. I've done problem 27 on the previous recording. 39, 41, and 43, I'm not that worried about. Okay, I'm not. They're just, I don't mean to minimize the importance of the problems by not doing them, but what I'm trying to get you to understand is I'm really concerned with right now, can you do integration by parts? Not can you do an integration by parts problem that comes straight from the 7th level of hell, according to Dante. So For those of you that have read Dante's Inferno, that made sense. For those of you that haven't read Dante's Inferno, that made no sense. So I'm not going to put one of those problems on your midterm. I'm not going to put one of those problems on your quiz. I'm not going to put one of those problems on your final exam. Why do they put those in the book? Should I always do them? Yes. Will you ever put problems like that on a midterm? Absolutely. I'm just not putting these on your midterm is what I've said. You should work those problems out. Those problems tell you, have I progressed all the way to where I'm supposed to have progressed using integration by parts? If you can fight your way through problem 39, do the integration by parts. They already tell you what your answer is, right? 39 says if you have the natural log to the nth power. We just did the natural log squared. So our n was 2, this one's n. You're going to be able to fight your way through that. It's exactly the same as the problem we just did, 23, except you don't have to evaluate it. And that's going to show you that you've progressed far enough to say to yourself, okay, I've got this. If you can't do problem 39, then you need to go back and do more integration by parts problems. That's how you're going to become competent at integration by parts. So problem 39 is a measuring stick, right? It's a measuring stick. Problem 41, you just use the problem 39 formula and plug in 3 for n. I mean, it's just literally a substitution problem. And then problem 43 is just a physics problem. For those of us who don't remember, distance is the area under the velocity curve. So we integrate velocity, to get distance traveled. So you're traveling there. How far will it travel in the first t seconds? So you're integrating for the first t seconds between 0 and t. If it was traveling for the first 15 seconds, it'd be from 0 to 15. And you're integrating the velocity function, which they give you in the problem. So that's going to be t squared e to the minus t. So how far does it travel in the first t seconds? Now here, if it was me, and you're evaluating this at t, I would not use the same variables here as I use up here. That's going to be confusing. Just make this a w, right? And then do the problem. We've already done that integral. That integral is, I'm looking for it here. I thought we did. If you go back and look at problem 16, we had an x squared e to the negative x. Now it was x squared plus 1, but we had an x squared e to the negative x. This is essentially the same problem as 16. Hence the reason I'm not going to go back and work through problem 43 for you. All right, so that completes the homework solutions for section 5.6. I hope you find this helpful.